All right, let's talk about atoms, molecules, and ions. So this is chapter 2 in our textbook, and we're going to be looking at the structure of atoms, how they combine into molecules, and how they form ions. And so when we talk about atoms, if you really want to read the history of how atoms were kind of discovered, that's not really ever something I focus on because um, this is chemistry, not history. But you can see all the interesting things people did in like the 1800s and all that in the first couple sections of the textbook. So if you're interested in that, it's there. But I will not be testing you or anything like that on those. We're going to kind of already have this idea of atoms in our head, right? You know, that they're pretty standardly covered in like 8th grade when we first learn about atoms in general. And we probably will remember that these are made of subatomic particles. And of course now we know that these subatomic particles are made of even smaller things called quarks. That's thankfully still beyond this course. So that's particle physics. That's more advanced stuff that we don't have to worry about. And so if we don't have to worry about the quarks, we can focus on the subatomic particles. And there are 3 of them. There are protons, neutrons, and electrons. And they differ in a few of their properties. We're going to see that protons, if we want to look at the mass of these particles, protons have a mass of about 1 atomic mass unit, so do neutrons. Neutrons are slightly more massive than protons are, just a little bit. And electrons are about 1/2000th of an atomic mass unit. So electrons really don't contribute much at all in terms of the mass of the atom. We're going to see that most atoms have quite a few protons and or neutrons. As we can see here, that the fact that these are 2,000 times heavier or more massive than electrons, that most of the mass is going to come from the protons and neutrons. 99.98% of it. So let's go ahead and look at these further. We're going to see that within an atom, if we look at where these subatomic particles are located within the atom, we see that protons and neutrons are in the nucleus. That's the center of the atom. And electrons are all over. I'm going to say that we generally say they're in orbitals around, but the orbitals are probability distributions, and we don't actually, have a fixed position on electrons. We have mathematical projections of where they are likely to be, but and what pathways they kind of are likely to follow, but we don't know exactly. We can't pinpoint and say, there's an electron right here, and that's something we'll see when we talk about the Heisenberg uncertainty principle. So I'm going to say for right now they're all over the atom. Everywhere except the nucleus, that is. So they are essentially making, the entire size of the atom is where the electrons happen to be zooming around at near the speed of light. And the protons and neutrons are within the nucleus in the very center of the atom. And then finally, we're going to talk about the charge. Protons have a charge of 1.602 times 10 to the negative 19 coulombs. It's the unit of charge. Neutrons do not have any charge, and electrons have the same charge as protons, but negative instead. Remember that charge can be positive or negative. There's not really a physical meaning behind that. There's no like positive and negative are relative terms. They don't exist. But they're the opposite. So we arbitrarily label one as positive and one as negative. We often, instead of using this actual charge in physical terms in coulombs, we actually sometimes just say +1 and -1 for charge. So instead of saying actual physical measurements of charge, we just say it's kind of like one charge unit, one electronic charge. And that's a +1 for protons and -1 for electrons. So more often we will use the +1 and -1 than the actual charge. But when you get into analytical chemistry, you'll see in physical chemistry that you'll more than often use the charge rather than, like in actual coulombs, rather than these kind of arbitrary ones. And so with these subatomic particles, which hopefully we have all seen before, we'll be able to talk about what happens with the various numbers of these that go into an atom. And so that'll be in the next couple of videos. But if we want to kind of focus right now on just the picture of an atom, if we wanted to have some sort of visual representation in our mind, we have a nucleus. That's that dot right there. And we have essentially this huge sphere of where the electrons could be. Remember, the electrons kind of zoom all over the place in different pathways and probabilities. But what's interesting is that this outer area is 10 to the 15 times as large as the nucleus. So the nucleus really is a speck. So if the nucleus has, a diameter, if it's spherical, it's got a particular diameter, the entire atom is 10 to the 15th power as large as that nucleus. As the radius of the atom, or the diameter we can say, is 10 to the 15th as large as the diameter of the nucleus. And 10 to the 15th, so let's see, that's quadrillion. I remember when I was first learning chemistry, we had the following kind of other visual. If we consider that the nucleus is the size of a grain of sand, we can imagine that grain of sand on the pitcher's mound at Dodger Stadium. And the rest of the atom is the size of Dodger Stadium. So the size of a grain of sand versus Dodger Stadium. So that can fit however many hundreds of thousands of people, right? Or tens of thousands. I don't actually know. But that's the idea. That's the scope of this. So that means that if all the mass is in the nucleus, and these electrons are these very, very tiny things zipping around in the size of Dodger Stadium versus that grain of sand, that means atoms are, 99.999999999999999% empty space. So that's pretty mind-boggling, right? I mean, where everything matter in the universe, which is made of these particles, is mostly empty space. Room for electrons to zip around. And so when you're feeling that kind of existential dread, thinking there's this giant void within you, that's true, because we are all indeed mostly empty space. And, just for another point here, interestingly enough, if we were to kind of condense all that empty space, if we just had the atoms as only nuclei, and there was none of this 10 to the 15th business, all the matter in the universe, if this empty space was not there, if it were all condensed together, would be about the size of a desk. like an office desk, not like a student desk, right? Just pretty mind-boggling. All the matter in the universe, how big the universe is, and how much empty space there is. If that empty space were not there, if it were all filled, it's the size of a desk. How absurd, right? Really mind-boggling. So I'll leave you with that. And in our next videos, we'll talk about more about these particles and how they influence our understanding of atoms and how we can classify them.